All right, hello everyone. Welcome to class. So today we're going to be discussing linked lists. I don't have a notepad file up, or do I? There we go. Sorry, these are not notes for your class. These were notes for my other class. So as some reminders, homework 5 is due Friday, 11:30 p.m. Homework 6, which will involve linked lists and heaps, which are topics we cover in today linked list, next Monday heaps. That is going to be due April 28th, which is the last day of class. So that's what we're covering today. There will, and I'm just going to preempt the question, there will be a quiz this weekend. Yay, quiz! Let me make sure. There's one other thing I just wanted to check real quick. Hang on. Sorry about that. Sorry, I'm stalling here. There is an in-class activity today, and yeah, the semester is almost over. So we have, I mean, I could just outline the next few classes. So today is linked lists. Friday, intro to trees. Next week is heaps, binary search trees, and then something else. I can't remember what it is. And then exam review. I actually can't remember what. It's on the course schedule. Who cares? Point is, there's only 5 classes left, counting today. So let's go ahead and jump into it. Are there any questions before we get started? So if I don't really do homework debugging at this point, I would say, will 2 quizzes still be dropped? Whatever our previous policy was, that's what our policy is. It hasn't changed. I don't know. I don't remember if that was 2 or if that was 1, but whatever that policy was, it hasn't changed. Will I miss you? I mean, I miss you guys now because teaching online is awkward and I don't enjoy it. And my cats keep messing up my lectures. Speaking of, you can see Stewie on the couch back there. He's taking a nap. Um, was there no partial credit for the question with multiple selection on the exam? Not so. However, it was graded. That's how it was intended to be graded. And if that resulted in no partial credit, that was how it was intended. I actually didn't have a hand in writing much of the multiple choice questions, so yeah. All right. So with that, no, you. So what do you have? What if you have 2 finals on the same day? So, the rule is, I believe, 3 finals on the same day you can reschedule. I don't believe, I believe with 2 finals on the same day you cannot reschedule, but I'm not certain of that. I'll have to check, but I'm pretty sure that's the rule. So if you have 2 finals counting ours on the same day, I don't think you can reschedule. I don't know yet what our policy is going to be because we haven't planned it yet. If I'm completely honest, so we'll try to get to that. Anyway, so today, and I apologize, I don't want to get into answering questions about the exam right now because the second I start answering questions about the exam, there's going to be like a billion questions on the exam, and I don't know the answer to any of them. So with that, um, today we're going to be starting talking about linked lists. We're actually going to finish, and the motivation of linked lists is as follows. So we've discussed how there's this thing called an array list that's implemented, um, that implements the list interface. The list interface lays out some methods like add, get, set, remove, contains, etc. That the array list is one implementation, and at Bedrock it uses arrays. The linked list is another implementation. We're going to get into actually how it's implemented, and it looks a little bit of something like this. And the basis is this thing called the node class. Let me move my head. There we go. And the node class, I actually have it implemented here in, once again, needing to move my head. I have it implemented here in Eclipse. This is a node class, and the node class is made up of two elements. We have some value, which is stored inside the node, and a pointer to a next node. So for example, on the previous slide, this is a node which contains the value linked and a pointer to another node. This is the basis of the node. It's two things, the data and where to find more data, where to find the next piece of information. Now, all lists end. There are no infinite lists. We can't store infinite memory, so we need some way to mark the ending point of our linked list. And the way we do that is by stating, hey, if there's no more information after this node, then the next pointer is going to be set to null. That is, remember that null is a memory address. That actually means nowhere. Null more accurately means nowhere than nothing. And so if the next pointer of this node points to null, that means it points nowhere. That means this is the end of our linked list. So our linked list just contains a series of chained together nodes with the last node pointing to null as its next pointer. Let's take a look at the code for this. You can see here we have an int node. This is a node designed to store an int value. So we have public int value as one of our two things we're storing, and public int node next, which contains our next pointer. And notice that the data type this points to is int node. This data structure is actually self-referential. It is recursive in nature, hence why we talked about recursion before this. And you can do a lot in linked lists with recursion, though we're not going to today. So we have public class int node. It contains a reference to an int node. And initially when we create a node, we pass in a value and we set next to null. That is to say there's nothing after this node. But then we just have standard getters and setters. Here's my getter and setter for value. Here's my getter and setter for next. Let's take a look at a use for this node, because by itself, a node is not a list. A node is a part of a list. So let's take a look at how this can be used. So the idea of the list class, the linked list class, is the linked list combines a series of nodes to form a list. Now, in order to keep track, and I need to move this for now. In order to keep track of every node, we actually don't need a new variable for every node. Here I have 7 nodes, but I only have 2 variables. And actually this one is not even needed. I don't need a tail. The only node that I need is a head. And the head node can be used to access every other node. Not necessarily directly, but indirectly. I can go from the head node to any other node. So you can think of the head node like the engine on a train, and the tail node as the caboose, and all these cars are linked in between them. They're linked to the car behind them. They effectively pull the car behind them. And so I can access these nodes by going, if this is my head node, then this node is head.next. And this node is head.next.next. And this node would be head.next.next.next. Now I want to be clear. The node is not the value. This thing I'm clicking is a node. It is not the number 5. The value of this node is 5. So if I want to get the value of this node, I would say head.next.next.next.value. As you can see here. So the list class does not keep track of every node. It only keeps track necessarily of the first node and sometimes the last node. Now I want to be clear, I've been saying a lot about .next. Today what we're discussing are called singly linked lists. Singly meaning there's only one link. Each node is linked only to its next node. It is not linked to the previous node. Now you can do that. It's a doubly linked list. But you can't link, but in this case, I'm not doing the previous node. Do you reference the tail node with, I would just say tail. So tail is the node, tail.value is 9, and tail.next is null. So it's node similar to index. Not exactly. See, an index is a number. And you can think of each node as part of the list, like you can think of each index as part of the array. But the difference is accessing an array is a constant time operation. Accessing an index of a list is actually a linear time operation. It is slower. All right. So now let's take a look. Let's take a look at an application of this. So we're all familiar with stacks. So I actually have, and by the way, I've already uploaded all of this code. I have already uploaded linked int stack. So this is an integer stack implemented with a linked list. And I only keep track of the head. I actually don't need to keep track of the tail here. So this is a simple application. And the idea is this is my field. It is my head node. Now, when I create my list, I'm going to say head is null. And the reason I'm saying head is null is because when I first create my stack, the stack is empty. And it's empty until I push things. So to that end, I have this method is empty. And is empty is a question. Is the list empty? And it's empty when head is null, and it's not empty when head is a node, when it's not null. So I can just return head equals null. That is either true or false. That gives me the true or false. So now let's take a look at push. But before we dig too deep into the code, let's actually look at an animation of that. So in order to push a node, what I need to do first is I need to create a new node. And this new node is going to store values. So whatever value is passed into the function push, notice it's an int, not an int node, but just an int. If value were 7, I would replace that with 7. If value were 13, I'd replace it with 13. From there, I've created this node, but I have not yet linked it into my list. So this is the first step, create the new node. From there, I need to add the node to the head, connect the node to the head. So first, to create the new node, I do the code int node equals new int node value. The second step is new node dot set next head. So new node dot set next head. That creates this link. From there, I now need to update the head pointer. Do linked list function like queues? They can, and we have an example of that. But they don't have to, the same way that they can function as stacks, but they don't have to. A linked list can function as a list. Lists can function as stacks and queues. So from there, I have this connected, but now notice this is no longer my first node in my linked list, right? And if this is no longer the first node in my linked list, then I need to update my head pointer. And the way I do that is I say head equals new node. That changes this pointer to point to my new node variable, as you can see here. So just to illustrate that again, I create my new node new node.setNextHead, head equals new node. Are there any questions about this? Does everyone realize how this added to the front of my stack? From there, again, we've talked about is empty. Which of these two lists is empty? Obviously list 2, so we can just say return head equals null. Now let's take a look at the pop function. So if we added when we push to the front of the stack, then when we pop, we need to remove from the front of the stack. Why don't we add to the end? Here's why. The reason we add to the front is this is a constant time operation. Notice there's no loop. But I'm not keeping track of the tail, and so because of this, if I wanted to find the last node, that would require a loop, and that would be constant time. And plus, if we keep track of the tail, we'll talk later about how in a singly linked list, removing from the tail cannot be done in constant time. So I'll get into that a bit later, but for now we're just adding and removing from the front. So let's take a look at how we pop. So pop, first, the first thing we're going to do is we're going to store our return value. So we're going to return what we're popping. So we're going to store this value into a variable called return value. There is no loop. That was my point. Adding to the front is constant time. So there's no loop. It's constant time. Adding to the end would not be constant time. It would be linear time because I would need a loop. Now I could keep track of a tail pointer and then adding would be constant time because I wouldn't need to find the tail, but removing from the tail would actually still be linear time. And I'll get into why in a bit. All right. So now we're going to store the value that we're going to output in a variable called return value. We're then going to say head equals head.next. What this does is this changes the head pointer. It was pointing here. Now it's going to point to this node's next node over there. And that's what happens. And let me undo that real quick, just that way. There we go. Then we return the value. The value 8 gets returned. Now, already here we have a problem, you may think, because this node is still here. My question to you is that a problem? Will this node cause any problems based on the code we have so far? No. It takes up memory, or does it? You see, the thing is, if this were programming in something like C, you would have to do memory management yourself. You'd have to delete the memory reference. But in Java, Java has a process called garbage collection. And I've always referenced the movie Langoliers or the Stephen King short story Langoliers, and nobody ever knows what the hell I'm talking about. So instead, I'm going to try a more modern pop culture reference. Here is what happens. Notice there is no variable pointing to this node. Head points here. Now you may think, well, there's no variable pointing to this node. But I can do head.next to get to this node. There is no previous, and so I can't say head.previous. This is a one-way street, so there's no way to reach this node. So here's what that's like. What happens to the node containing 8? It gets picked up by Java garbage collection. And it looks a little something like, hang on, I have to do this. Oops. It looks a little something like this. It gets disappeared. Just to show that again, Java garbage collection just simply removes that reference. It's not needed anymore. Too soon? My bad. So the point here is Java actually has a mechanism called garbage collection, which will look for unreferenced memory, and it will delete it. That is to say, release the memory back to the computer. So you don't have to worry about that in Java. When you get to 2150 and you start using C, you will actually have to delete that memory reference in order for it to work correctly. All right, so that is how that goes. Now, I want to take a minute and I want to ask a question. Let's say we want to implement a queue. We have two choices with a queue. We can either add at the front and remove from the tail, or we can add at the tail and remove from the front. So option 1, add new values before the head and remove from the tail. Option 2, add values after the tail and remove from the head. Which choice do you want to go with? 1, 2, or 3, 4, it doesn't matter. Type 1 if you're option 1, 2 for option 2, 3 if you don't think it matters. Are there consequences to garbage collection? It takes up processor time. I mean, so one reason that a lot of languages don't have it is they're saying you're a real programmer, you should be able to do it yourself. But the problem is if you don't do it correctly, you end up with something called memory leaks. And a memory leak is when your program consistently adds memory over time. It consistently adds new memory. And as a result of that, because you never release memory, the system will eventually, if running long enough, actually run out of memory and crash. And there's a story I'll tell on that in a second. Most of you are saying 2, and 2 is actually the correct choice. And here's why. Let's focus on the remove operation. Let's say I need to remove from the head. Well, that's easy enough to do. I just showed how to remove from the head, right? You say head equals head.next, and then you're done. I've removed from the head, because that node will disappear. What about removing from the tail? What do I set tail equal to? Because I would have to do this, right? I'd have to say this. Okay, write one line of code that does that. Write one line of code that says go from tail to here. And the answer is you really can't. You need a loop. You have to have a loop. Right, it's not a doubly linked list. And here's the thing. You may think, well, why don't we do a doubly linked list? A doubly linked list uses up more memory. Also, it's more complicated from a code perspective, and this is an intro to linked lists, so I'm going to try to keep it simple. So, we're actually going to go with option 2. We are going to enqueue at the head, we're going to enqueue at the tail, add values after the tail, and we are going to remove from the head. Now, again, you're right. If this were doubly linked list, it wouldn't matter, but it's not doubly linked list, and a doubly linked list does use more memory than a singly linked list. All right. So let's implement the queue. What are linked lists good for compared to array lists? Adding to the front. So if all your operations are what we call DEQ, that is double-ended queue, that is inserting at the front or inserting at the back or removing from the front or removing from the back, a linked list will be faster than an array list. If you do anything else, any access in the middle, array list is significantly faster. Correct. We never have a grow if necessary function with a linked list because they can theoretically be infinite size. Now, of course, practically your computer only has so much memory, and you can only have as many nodes as your memory supports. The other thing is each piece of data in a linked list does individually use more memory. Forgive me for 1 second here. Sorry about that. Had to blow my nose, and I never like to do that on camera because that's kind of gross. Of course, I just told you that. Whatever. I'm bad at people. Anyway. So one thing I want to note is let's take a minute and let's look at our queue. So I've uploaded string queue. And there's a couple reasons I did a string queue. The first is the node class stores a string, not an int. And the point is, we can literally store anything we want in the node. You can even store more than one value in the node. The point is, you always have some value. You can store any... I could make a linked list of Pez dispensers. Pardon me. But you always have a next node. And if you want doubly linked list, a previous node. But the other thing is, I this time am effectively going to make these public. And notice that this is an inner class. I'm defining this class inside of my class string queue as private. And the reason I'm doing this is that this class only exists in string queue and only needs to exist in string queue. So string node takes any object. No, string node is a class I'm defining that only takes a string. The point is, I could just as easily have called this car node and made this a car. Or I could just as easily call this a Pez dispenser node and have made this a Pez dispenser. The point is, I can store any value in a node by making the node store what I want it to. But in this case, I'm just going to use a string. Notice this is defined as an inner class here. Would it work with protected instead of public? It would actually work with private instead of public too, but that's neither here nor there. The point is, I actually don't even need the public here. I just didn't want to confuse people, so I quickly added public. Now, the advantage of this, the reason I did this, I made these values public, is I don't need getters and setters, so I can just say things like tail.next equals new node, not tail.setNext. So this lets me directly access the values. So now with our queue, in addition to keeping track of our head, we also need to keep track of our tail. Additionally, we can also keep track of things like our size. Now, we could derive our size, but I want to actually keep track of it and show us how to do that. So let's start working on this string queue. So the first thing is look at enqueue and dequeue, and I'm not going to take too long of this. You'll notice that dequeue pretty much works exactly the same way. Here, this works exactly the same way as pop. We store the value that we're returning in a variable. We say head equals head.next. We return that value. In addition, because I'm keeping track of size as a variable, I would just say size minus minus, because if I'm dequeuing a value, obviously the size is decreasing by 1. But there's one other thing I need to take into account. Let's say that my string, and for now I'm just going to move some things around here. Let's say that this were my list. If this were my list, and please ignore all the other nodes over here. Here, I'll help you. If this were my list, there's something else I need to take into account. Because I can say head is head.next, and head is null, and then my size is going to be 0, but am I done? If I dequeue the last value, there's one more line I need to write. Because I want this node to disappear, and it's not disappearing yet. Why is this node not disappearing? This is if the list is size 1, and we're dequeuing the last value. Right, the tail points to it. So what I need to take into account is if my list is now empty, that is, if I should have an empty list, then I also set tail to null. And so that's what I do here. If is empty, that is to say that is empty now is calculated by size. So if I've removed the last value, then I say tail equals null. If, however, the list is not empty and this were my list, when I dequeue, I would say head is head.next. And notice here I don't need to update my tail pointer at all. So I only need to update the tail pointer when tail points to null. Or I'm sorry, when the head after dequeuing points to null. Excuse me. I only need to update the tail pointer to null if the list is now empty because I dequeued the last value. And again, I'm kind of speed running this code. This code is already uploaded. Please take some time to read it. With enqueue, I need to take into account what if my list is empty, because there's two possibilities. So if the list is not empty, I just add it to the tail. I say I create my new node. I say tail.next equals new node, and I then say tail equals new node. So to illustrate what that would look like, let's say, and I'm going to cheat here, let's say that I created a new node 9. This is my new node, and I need to add it. The first thing I'm going to do is I'm going to create my new node. I'm then going to say, and by the way, it's pointing to null too because it's a new node. I'm going to say tail.next equals new node, which updates that pointer. I then say tail equals new node, which updates that pointer, and now you'll notice I'm basically done. So that's the enqueue, where we add at the end. But, again, I have to take into account where what if head and tail are both null. That is to say, if my list is empty. When I create the new node, that means that I went from 0 to 1. If I only have one node, it is both my first node and my last node. So if the list is empty, I do this. Otherwise, I do this. But I create the new node before that because I always do string new node. Any questions about enqueue or dequeue in the string queue? The last node automatically points to null. So the reason the last node automatically points to null is this. Whenever I create a node, by default, it points to null. So that's not magic. Well, actually, I should say, even if I didn't have this line, by default it will point to null because the default value of every object is null. But so that's why when I create the new node, when I created the new node, it already pointed to null. Okay. So now what I want to talk about is this method here, toString. What this is going to do is this is going to print my node. And to illustrate how this works, and by the way, I have this test already here. I enqueue linked lists are fun, and then I print the queue. And I want to show you what it looks like. So for now, let's just comment out the rest of this code. And when I run this, it prints my head node points to linked lists are fun. So this is the head pointer, which points to link, the node containing linked, which points to the node containing lists, which points to the node containing R, which points to the node containing fun. I didn't add the last pointer null in my print statement. I could, but I didn't see a reason to. So how does this work? And at root of this is the question of how do we loop through a linked list? And the way we do that is we create a traveling node. Oops, sorry, not what I was trying to do there. A traveling node. And the traveling node T is a node that, think of this like a train. If this were a train line, so we go to station 8, then station 6, 7, 5, 3. This is a passenger riding the train. And the passenger boards at the head, and it rides until the end of the line, which is null. So, taking a look at this loop, first, we create our traveling node T, that is string node T equals head. We loop while T is not equal to null, and every step along the way we say T equals T dot next. So the first time through the loop, I'm going to go through this and I'm going to start at the head. And T is not null, so I'm going to enter the loop, and I'm going to say S plus equals, and then it's an arrow plus T dot value. Next time through the loop, I say T equals T dot next, and that's what it looks like. T has moved to the next node. I then add 6 to the string. I say T equals T dot next, and I move to the next node, and so on. And a few loops later, I'll reach the last node. I still enter the loop. I still print 9. And then I say t equals t dot next. And now t points to null. And because t points to null, and we loop while t is not equal to null, the loop terminates. We don't re-enter. Here, let me make sure everyone can see the stop sign. Oh, I'm melting. That was a really stupid joke. Anyway. That's when we reach the end of our loop. So this loop body here is a pretty standard for loop to loop through a list. Are there any questions about that? I'm trying to pop my head up here. I have risen. Are there any questions about that? How would this work for a doubly linked list? Exactly the same way. Because you can start at the head and still loop through. Oh, no, so what you're thinking of, that's not a doubly linked list, that's a circular list. And what then you would have to do is you'd have to add in some logic for the second time that you reach the head node. Which you could do, but I'm not going to get into circular linked lists today. I mean, you could add in some logic, just say, hey, is this the head node, and have I been here before? And if it is the head node, and I have been here before, then I exit the loop. Something like that. But circular linked lists are not particularly practical. Because you already have the deck. Like, the reason you do arrays as ring buffers is so you can have deck behavior and constant time. But you already have deck behavior and constant time with a linked list. To find if the list contains something, you are asking a great question. Can you use contains, or do you have to loop through the entire list? So remember, in this case, we're making our own linked list. So are you guys familiar with the meme, like, you know, Mom, can we have a blank? Well, we have a blank at home. The blank at home, you know, blank. All right, that meme. So there is something in Java, and I've shown this before, called a built-in linked list. And I could do linked list string. I could do linked list string equals new linked list. And this is like out of the box linked list. Like, this is going to the toy store and buying a linked list. And you're like, hey, Mom, can we have a linked list? And Mom says, no, we have a linked list at home. And this class is the linked list at home. We've implemented it ourselves. So, yes, you can just do this. But the point of this class is not to teach you how to do this. The point of this class is to teach you how the linked list works. Because you already could have done this. I've talked about this before. This isn't new. This part, how the linked list actually works under the hood, that's the point of this lecture. So should you generally implement your own linked list? No, generally you shouldn't. Generally you should use this. But you have to understand how it works in order to appreciate where a linked list is better than an array list. Is that the same as the linked list that is in Homework 5? You got it. In Homework 5, we're not having you implement a linked list. We're giving you a linked list object that is already acting as a queue, so you don't have to worry about how that works. So you are exactly on point, K-Stat. So the point here is to illustrate how it works, not, oh, wow, linked list, this brand new thing. I've mentioned it existing before. I'm just trying to get to the how of a linked list. All right, but now you're asking a great question about contains. So I cannot do q.contains. And the reason I can't do q.contains is because I have not written my own method called contains. So I would have to write my own method called contains. And wouldn't you know, crazy me, I almost predicted this question. No, there is no this dot contains, because again, this is my own linked list. This class is my own linked list. So I can't use methods I haven't implemented. This is home-cooked linked list. If I want I can home make a pizza. It's probably going to be a pretty crappy pizza. I'm not a good cook. I don't have a great oven, right? It's not going to be a great pizza, but it can work as a pizza. I can add things to it to try to make it more like a pizza. This is like going to College Inn and getting a pizza, because College Inn pizza is really good. And I know I just probably started a pizza war in chat. But my point being, this is delivery. This is DiGiorno. And let's all be honest, DiGiorno's not as good. All right, delivery, DiGiorno. DiGiorno doesn't have a contains method unless I add a contains method. So that's why there is no contains method yet. But wouldn't you know it, I anticipated this question. And here we wrote a linked list, and wouldn't you know it, here's a contains method. And we're going to actually look at this method here in a bit. So with that, I have written a class myList. This code is actually part of the in-class activity today, so it might be worth paying attention. Let's pop to the slides, and let's take a look at how the get method works. So up until now, and notice in Q, I didn't have any kind of get method. There's no get method, and that's because it's a queue. I don't need to get values. I only need to enqueue and dequeue. But if I want to make a general list, well, a general list has a get method. Get a particular index. Where is it? I was on the wrong file. This method is going to get the value stored at some index. So let's take a look at how this method works. So if this were my list of ints in this case, if this were my list of ints, and I called get, let's say I called list.get4. So that means I need to get the value at index 4. Now you and I as human beings can count, and we can say, okay, this is 0, this is 1, this is 2, this is 3, this is 4. Give me the value 3. That's what you and I as human beings could do. But we can't do that in a code level like a human being. We have to tell the code how to find the 4th node, or the index 4 node. So what I do is I store my value index into the variable index from the argument, and I create my traveling node, same as before. And now notice I did a while loop. You don't have to do a for loop. You can do a while loop. And what my while loop is going to do is it's going to loop while index is greater than 0, and every loop it's going to decrement index, and then say t equals t dot next. So I say, enter the while loop. Here we go. We take one step forward, t equals t dot next, index minus minus. Now notice index is 3. We're on the next node. Take another step forward, index is 2. We're on the next node. Another step forward, index is 1. We're on the next node. Finally, index is 0, and because index is 0, we don't re-enter the loop. So t is pointed to our node, index 4, and we just simply return t.value. So that's how we can implement a get method. So this loops through a linked list, but we don't need to loop all the way through. We only need to loop to index 4. And by the way, you can code this any number of ways. This is not the correct way to code it. This is just a way I coded it that was easy to illustrate. Now, I want to take one other thing into account. Is the head and tail node also a node like T? It is. T, head, and tail all have the same data type. T, though, only exists inside of this function. T is not a class, or it's not an instance variable. T is a local variable only to this function. So once I leave this function, T doesn't exist anymore. But now I want to take a look at one other function you've used before in a linked list. So we've talked about the add function, and this would add a new node to the end of the list. But what if we want to add the node somewhere else? We have this function add, which takes in an index to add the value at and a value. This is a function that the list interface has. And it turns out that this function can be fairly difficult to add. The first thing is, and by the way, we had this in get, we have a check to make sure the index is valid. Now, normally you would say is greater than or equal to size. That would be out of bounds. But because we're adding a new node, we can add a new node at size. We can add it after the last node by saying index equals size. We create our new node. If the list is empty, that means that we're adding a node. That is the only node, so we do our standard list add if empty. Else, if the index is 0, we add at the head. That's nothing new. We've done that. Else, if the index is size, we add at the tail. Nothing new. But the question is, how does this code work? Because this is adding in the middle. And here, adding into the middle, there are some unique complications. Luckily, I have an animation for that. Let's say we wanted to add 417. What this means is that we are adding the node containing the value 17 at index 4. So this is how our list would look before the call. This is how our list would look after the call. The question is, how do we get from here to here at a code level? So let's take a look. So by the way, we were talking about adding at the end, so let's focus here. We want to add 17 there. So how do we do that? Oops, sorry. First, we create our traveling node t at head, and then we have a loop. And notice this is the same loop as get. Exact same loop, except one thing. We're not stopping at the node of index 4. We're stopping before where we would add it. So if we're adding the node here, we actually want to stop not at 4, but at index 3. And so because of that, I'm not going to loop while index is greater than 0. Rather, I'm going to loop while index is greater than 1. Because I'm stopping before where I would do the add. So let's work through this. Index is 5. We have the value t at head. We say index minus minus t equals t dot next. Index minus minus t equals t dot next. Index minus minus t equals t dot next. And now we stop. So that's the first step. Now from there, we actually need to insert that new node. So we have this new node currently just hovering in space. And its next pointer currently points to null. Now I have to be careful with how I do this. This is actually rather important. Let's say I accidentally did the following. Let's say I said, okay, t.next equals new node. Oh, sorry, you're correct. I had a typo in the slides. Yeah, the index, sorry, should have been 4. That was just a typo. So index was 4. The rest of the slides were fine. So if I were to just say this, if I were just to say t equals t, or t.next equals new node. So I said t.next equals new node here right away. What have I just done that's really, really bad? What did I just do that's really terrible? I replaced a node. That's not a problem. I deleted not everything, but all of these nodes. Let me ask you, what's referencing these two nodes right now? What's referencing these two nodes? Nothing. And so they're going to get garbage collected. They're going to get deleted. They're going to get snapped, to reference the meme I referenced earlier. Spoiler alert, by the way, if you haven't seen that movie yet. And if you don't know what movie I'm talking about, if I tell you, it's going to ruin the movie. So anyway. So because of that, what I need to do first is I need to say new node.next equals t.next. So the first thing I need to say, I need to create this link. New node.next equals t.next. That's the first step. This is going to make sure my link is preserved. So new node.next equals t.next. Then the second step is to say t.next equals new node. And now if you'll look, I'm done, right? I've created the new node. What is next again? Next is the pointer that every node has. So that's the next is every node has a value and it has a next. And next points to where to find more data. So it's the pointer that every node has. And that's add. So now, the last thing I want to show you is this method contains is implemented in a fairly straightforward way. Let's just take a look at it. We have a loop. This loops over every value of the node. We've written this for loop before, so I'm not going to dig into it. And then we say if t.value equals target, return true. Because if we find the value, then we found it. We can stop there. We can return true. If we get through the list, having never found the value, we return false. Your in-class activity today, use this code heavily. Use contains heavily, but I don't want you to return true or false. I want you to write the function find, and find is going to return the index, the numeric index of where the first instance of target is. So here we're just returning whether or not target is in the list. Here you're returning the index of the node that target is at. And if target is not in the list, then you return -1, sentinel value. And no, don't try to do any kind of binary search. One, I'm not saying the list is sorted. Second, binary search of the linked list just doesn't actually work. It's not more efficient. So just do a linear search. So that's your in-class activity today. From there, I'm going to have to end the lecture because we're at time. I've already gone over by 2 minutes. Apologies. But are there any questions? So this is the only thing you're implementing. You don't have to implement the rest of the class. I do have already a test case down here for find, where when find is implemented as it is, you're going to get -1 for both of these. Once you have it working, it should return 6 and -1. So that's your in-class activity. Are there any questions? Could you use a list iterator instead of a traveling node? You cannot, because the class I wrote does not implement iterator. So the iterator doesn't just exist. You have to add it. Now the out of the box, once again, the Java linked list is something that Java created that has all the features you could think of. That has implemented iterator, and so it has a iterator object. But we have not implemented an iterator, and I'm just not going to get to it today. So you can't just use an iterator. You do need to use a traveling node for this. It also means you can't do a for each loop. You have to, like, that is, you can't do something like for int x in head. That wouldn't work at all here. Again, the point of this class is not to say you should always create your own linked list. You shouldn't. The point is to say how the linked list works and to give you some practice with building one yourself. Because that's what homework 5 is going to involve. Stuart is still sleeping like a little angel back there. He's my buddy. Oh. All right. Well, I will cut it off there. Thank you all for watching, and I will see everyone Friday. Take care.